Let's look at the heat equation still on the semi-infinite domain, so just for x positive. But this time we'll throw in a non-homogeneous boundary condition. So how do you deal with this? Well, turns out, once again, we can reduce it to something we've already solved. So let's put v equal to uxt minus gt. So effectively changing variables. So u is going to be v plus g now. And what we get is making this substitution into the differential equation. We get vt minus we get that v satisfies vt minus k vxx equals minus the t derivative of g, but g is a function of a single variable, so I'll just write g prime. And that if we look at the initial condition, g is going to pop up here as well, but that's fine. It just changes phi by a constant, so nothing really different there. And then the cute part is that it disappears from the boundary condition. So now we've converted into something with homogeneous boundary conditions. Okay, so if you're thinking about like what just happened here, imagine that we're sort of vertically adjusting our frame of reference. Right? So as g increases in the original problem, imagine recalibrating by moving the entire resulting heat surface. And so if g is going upward, then you'd need to shift the heat surface downward. And if you did it just right, then you could keep the left-hand edge, in other words, the boundary right along where x is equal to 0. You could keep the value of the heat surface at 0. And so this recalibrate by shifting downward part right here is technically you're forcing it down by the derivative. Okay, so now we've got a problem for v, and now v can be found using Duhamel's principle. And by the way, this little discussion in the text, this actually shows up at the end of 2.5.